The signal arrived without fanfare, no blaring alarms, no emergency broadcasts. Just a quiet cascade of data streaming across a monitor in Cambridge, England, the photons that had been traveling for 124 years, finally arriving at the only instrument in human history capable of reading them. Dr. Nico Madhusudan leaned forward in his chair. The transmission spectrum on his screen showed something his models had theorized for years, but never actually expected to see. Buried within the atmospheric fingerprint of a distant world, two molecules were glowing like ghost signatures in the infrared: dimethyl sulfide and dimethyl disulfide. On Earth, those molecules are produced by exactly one thing: life. Marine phytoplankton, ocean bacteria, the invisible, teeming biological machinery of a living world. And there it was, 24 light years away, whispering. The confidence level wasn't marginal. It wasn't a flicker of noise at the edge of detection. The probability that this signal existed purely by chance was 0.3%. In other words, a 99.7% certainty that these molecules were real, present, and sitting in the atmosphere of a world orbiting a dim red star in the constellation Leo. The team would later call it a revolutionary moment. The first time humanity had ever seen potential biosignatures on a planet within a habitable zone. A planet that, according to every model they could run, might be covered in a global ocean. A world that some scientists had begun calling a Haitian world. Hydrogen atmosphere. Ocean beneath. Life possibly everywhere. This is a story of K2-18b and everything it might mean. To understand why this discovery matters, you have to understand the silence that came before it. For decades, humanity has been scanning the sky with every tool it could build: radio arrays, optical telescopes, infrared observatories, listening for something that never came. The cosmos had remained obstinately, beautifully, maddeningly quiet. The Fermi paradox, the contradiction between the mathematical near certainty that life should exist elsewhere and the complete absence of any evidence, had become one of science's most unsettling open wounds. Then came the James Webb Space Telescope, launched on Christmas Day 2021. Webb wasn't designed to find life. It was designed to look back to the first light of the universe, to study the formation of galaxies, to peer into stellar nurseries. But its instruments, and specifically its near-infrared and mid-infrared spectrographs, turned out to be extraordinarily sensitive to something else entirely: the atmospheric chemistry of distant planets. When a planet passes in front of its star during what astronomers call a transit, the starlight filters to the planet's atmosphere before reaching our telescopes. Different molecules absorb different wavelengths of that light. Carbon dioxide leaves one fingerprint, methane leaves another, and dimethyl sulfide, the chemical signature of ocean life, leaves a fingerprint unlike anything that should exist on a lifeless world. Webb could read those fingerprints with a precision no telescope had ever achieved before. K2-18 had first been detected back in 2015 by NASA's Kepler Space Telescope, a routine discovery among thousands, cataloged and filed. It was a sub-Neptune, about 2.6 times the diameter of Earth, and roughly 8.6 times its mass, orbiting within the habitable zone of a red dwarf star designated K2-18, far enough from its star that liquid water could exist, close enough that its surface wasn't a frozen wasteland. For years, astronomers assumed worlds like K2-18b were inhospitable, too large for a rocky surface, too thick in hydrogen to support the kind of atmosphere life supposedly needed. Then a team at Cambridge ran new models, and those models suggested something extraordinary. What if K2-18b wasn't a failed gas giant? What if beneath that thick hydrogen envelope there was an ocean? A planet-wide, unbroken, endless ocean? The idea had a name now: a Haitian world, from hydrogen and ocean, a class of planet that had never been confirmed before, theoretical, tantalizing, sitting at the boundary between what we knew about habitability and what we had always assumed. Batusadon's team pointed Webb at K218b in 2031st time. The results were startling. Webb's instruments detected methane and carbon dioxide in abundance. Carbon-bearing molecules that, together with a notable absence of ammonia, strongly suggested the presence of a vast liquid ocean below. The ammonia should have been there. In a hydrogen-rich atmosphere with no ocean, it would have been. Its absence meant something was absorbing it, something enormous, liquid, and covering the entire planet. Then came the dimethyl sulfide hint. Faint, uncertain, barely rising above the noise. A ghost of a signal. Enough to make the team pause, not enough to announce, so they came back. In April 2024, they pointed Webb's mid-infrared spectrograph, MIRI, directly at K28EB, a different instrument, a deeper look, and when the data came back, the ghost had grown into a presence. The signal for dimethyl sulfide and dimethyl disulfide had risen to 3 sigma confidence. In physics, 5 sigma is the gold standard for a confirmed discovery. 3 sigma means the probability of the signal being random noise is 0.3%. The molecules weren't just hinted at anymore. They were detectable, measurable, real. And here is the fact that changes everything. On Earth, there is no known abiotic process. No volcano, no lightning strike, no mineral reaction, no solar radiation that produces dimethyl sulfide at scale. The only known factory for it on our planet is life. Phytoplankton blooming in sunlit oceans, bacteria metabolizing in the soil, billions of microscopic organisms invisible to the naked eye, exhaling this molecule as a byproduct of simply being alive. But there was a harder fact underneath that. Science does not leap, it inches. Several independent teams immediately moved to reanalyze the same Webb data. Jake Taylor at the University of Oxford ran his own spectral analysis. A NASA-led team at the Jet Propulsion Laboratory, led by astrophysicist Renyu Hu, with Madhusudan himself as a collaborator, combined 4 new sets of Webb observations with the original data and applied a different statistical method called Bayesian analysis. The result was nuanced. The NASA study found a tentative DMS signal at around 2.7 sigma, slightly lower than Cambridge's 3 sigma, but still present, still unexplained, still sitting in an atmosphere on a planet inside a habitable zone, wrapped around what might be a world ocean. Other scientists raised different concerns. Researchers had detected dimethyl sulfide on a comet in archival data from the Rosetta mission, a cold, lifeless rock hurtling through interstellar space. Lab experiments had shown that ultraviolet radiation from a star, shining through a simulated hydrogen-rich atmosphere, could produce DMS through purely chemical reactions. The absence of ethane was flagged as a potential problem. If biological processes were producing DMS in the quantities detected, ethane should also be appearing. It wasn't. This is not the story falling apart. This is science working exactly as it should. The signal is real. The debate is about what produced it, and the only way to answer that question is to keep looking with more observations, longer exposure times, different instruments. Madhusudan's team estimated that 16 to 24 additional hours of Webb observation time could potentially push the detection to 5 sigma. A true, confirmed, undeniable presence. That observing window is coming. Stand back for a moment. Step away from the data, the sigma levels, the spectral models. Think about what this actually means for the entirety of recorded human history. Every living thing we have ever known about existed on one world. A single pale blue dot, suspended in 4 billion years of cosmic indifference. We built civilizations and wrote philosophies and sent spacecraft to the edge of the solar system, all while carrying this quiet, unspoken assumption that we were alone, that life somehow was an exception. A miracle. A statistical improbability so rare it had only happened once, here, and would never be found anywhere else. K218b is 121 light-years away. In cosmic terms, that is our immediate neighborhood. The Milky Way is 100,000 light-years across. We are talking about a star that is, relatively speaking, just down the street.